My name is Peiqing Chen from Boston University. Today, I'm going to present this paper, Precise Error Estimation for Sketch-Based Flow Measurement. Nowadays, Sketch has become a popular approximation method for network telemetry. Sketch has the advantage of using small memory to achieve high accuracy in measuring network telemetry. And the popular sketches include counting sketch, short for CM sketch, count sketch, CU sketch, etc. And they can support a wide variety of tasks, including heavy hitter, heavy changes, burst detection, and also flow size, flowlet measurement. However, Sketch has a major drawback in the errors and hard to predict. Currently, the analysis of sketches provide rather loose error bounds, and these loose error bounds can do harm to the real-world applications. In this example, the CM sketch is deployed on a network switch, and it reports a flow size estimation of 120, and the error bound is 100. It means that the actual flow size should fall in the interval of 20 to 120. Let's say if we are going to perform large flow detection and set the threshold of large flow as 100, it is rather difficult to deduce whether this flow belongs to a large flow or not. In this page, I will show how the error is generated in the CM sketch and its original error bound. CM sketch basically is composed of D rows and W counters per row. Each row has an independent hash function. When an item EA arrives, hash function computes one counter in each row and simply plus 1 to the counter value. In this case, item EA and EB, they can be hashed into the same counter in a row. This caused hash collision, and the error of CM sketch is generated. Graham-Collmodel gives an error bound based on Markov inequality for CM sketch. The error bound is linearly correlated with the total packet count. In practice, this original error bound is rather loose. In this example that we test with real-world traces, it shows that the ground truth error bound is about 800, and the original error bound is around 3000. Then we come up with a question: can we precisely estimate the error bounds at the query time? Here, precise not only means tighter than the original error bound, but it also means near optimal. We want our error bound to be close to the ground truth. And this paper gives an answer, yes. And we think that this will gain better trustworthiness on the sketch-based approximation results. Our key insight is that counter value distribution can reveal error distribution in a CM sketch. We first show by a simple case, one-row CM sketch. Here, when we are inquiring a non-existent flow whose actual size should be 0, it refers to the hashed counter in the CM sketch, and the counter value is 10. The sketch returns the result 10. And in this case, the error is 10. We have the statement that in a one-row CM sketch, the error distribution of non-existent flow is exactly the counter value distribution, which means the CDF cumulative distribution functions of the two distributions are exactly the same. In this row, we first sort all the counters based on their values from small to large, and we pick the largest W over E fractal as our error bound. Our error bound is simply a counter value in the CM sketch, and then we extend it into the more general scope multi-row scenario. And in this paper, we prove that the error distribution of any arbitrary flow is rather close to the counter value distribution in any row. We show that in the paper, the counter value distribution in any row, they are much alike. Thus, we are able to use something easy to find, which in this case is the counter value distribution and its fractal, to approximate something that is unknown, which in this case is the arbitrary flow error distribution and the error bound. So for the algorithm, we show by a case of CM sketch with 3 rows and 8 counters per row. Here, we arbitrarily pick one row, say the first row, and we sort all the counters in this row. Then we pick the largest W over E fractal as our error bound. In summary, at query time, our error estimator is simple to just look to the largest W over E fractal in an arbitrary row of the CM sketch. Also, our error estimator can extend to other sketch algorithms, for example, count sketch and CU sketch. For the experiment, we used 3 real-world traces, KIDA data center trace, DDoS attack trace, and 1 synthetic trace, and the metrics are original error bound, our error bound, and the ground truth error bound, their performance under different traces. We first experiment on changing sketch memory, then we change the trace size, and lastly, we change the trace skewness. All these 3 experiments show the same result, that our error bound is far tighter than the original one, and our error bound is very close to the ground truth, which means it is near optimal. There are many potential applications of precise error bounds. For example, when you are doing dynamic resource allocation for sketch-based measurement to achieve targeted accuracy, a tighter error bound can help you save memory resources compared with a loose error bound. Secondly, it can improve load balancing. For example, in a load balancing systems, the sketches are deployed on the switches, and a better detection of the hot items on switches can help you more precisely and effectively store the heavy hitter or hot items on switch caches, then improve the whole system efficiency. In conclusion, the original error estimation of CM sketch is very imprecise. We, in this paper, designed an error estimator that generates a near-optimal error bound for sketch algorithms, including CM sketch, count sketch, CU sketch, etc., under all circumstances. And a more precise error estimation can help a variety of real-world applications, including resource allocation, load balancing, etc. Thank you for listening. I'm happy to take your questions.